All right, so for today's meeting, um, we're going to talk about surds and exponents. And these are very, very, very easy things. The issue with it is just that there's gonna be a lot of there's gonna seem to be a lot of formulas going on. But in reality, if you practice a lot, it's very easy because it's just like the same. How do you say? If you practice a lot, it's going to be very intuitive and pretty much repetitive because it's just the same thing. Okay, so for the general terms that you need to know is surds, radicals, and also exponent terms like base and exponent. Radical is this sign. Anything with this particular sign is called a radical. And usually inside there's like a number, like 2 or 3 or x. And then for surd, a surd is what you call a radical with a number when you can't turn it into a whole number. So usually they're the ones that stays as radical. Like for example, if you have square root of 4, you can turn it into 2. So this is not a surd. But the ones that stays in radical forms is called a surd. Also, for side note, radicals can actually be expressed in terms of exponents, and it's usually written like this.
Yeah.
So
That's good for calculus.
Yeah, it is very, very nice. Kind of like this kind of writing. So in this form, the number two is called a base, while the exponent or the tiny numbers above it is called the exponent. So usually what's happening in this expression, for example, if you have a square root of 5, is that if you try to expand it, you have a times a times a times a times a. Wait, times a. So wait, times a. So you're gonna have 5 a's multiplied to itself by each other. And because this is very long, we usually compress it by just writing a with the square root of 5 above right here. But there's also like little things that you can do with this, and it will be seen later in the future, such as how a to square root of minus 1 becomes 1 per a. Okay, so I think I should just go back to the surds before I go all the way too far from it. Okay, so the thing with surds is that if you have surds with the same inside, or I think the same base, multiplied by itself, you will be able to remove the radical. And this is like, I think this is a very interesting notion, because if you have square root of 4 and then you want to like break it down into prime numbers, you have 2 times 2, and then you can also, this means you can get something like a times square root of a, which is square root of 2 times square root of 2. Then it becomes 2. And I think this is something that like you should really keep in mind when you do some questions relating to indices and surds. Because, for example, if you have a big number such as 240, square root of 240, you can just do something like 4 times 6 times 10. Wait, no, sorry. Yeah, 4 times 6 times 10. And then you can break it down further into 2 square root of 4 times 3 times 5. And then through this, you can easily know that you can take this out, since this is like the equivalent of 2 to the square root of 4 times 3 times 5 to the power of 1/2. And if we follow the rules of exponents, you can break this out and pretty much turn this into 2 to the power of 2 times 3 times 5, and they each have a power of half. And if we write it back into the radical form, we can get 4 to the square root of 15. So it's so breaking the numbers inside down into like prime numbers, usually I find it's a very good way to simplify surds into its simplest form.
Mm-hmm.
And then for rationalizing the denominator, so there are times when the surds are under the fractions like this. Let's just say this is 1 over square root of 3. And you want to and if you want to have, assuming this, the question is 1 per 1 over 3 plus 2 per 3, then you have this weird surd down here. And you would want to remove the surd because it's underneath. And an easy way to remove it is just by multiplying it with square root of 3 over square root of 3. So a surd of itself. The reason why you can do this is because square root of 3 per square root of 3 equals to 1. So it's kind of like multiplying this by 1, but it's in form of a surd. It's kind of like, it's also like the same thing as writing 4 over 4 equals to 1. Yeah. It's just like kind of like one of those algebraic manipulations. So if you do that and you move it up, you will get square root of 3 over 3 plus 2 over 3, and you'll be able to easily add up this and get 2 plus square root of 3 over 3. And then the next part is maybe for some people the trickier part when it comes to having surds. So okay. For example, we have 5 over yeah, 5 over 2 plus square root of 2 plus square root of 7. And you this this surd is kind of hindering you because it's down here, not above, right? And if you want to remove the surd, you can easily do it by so you can easily remove it by multiplying itself to this form, but this time with the opposite sign of this. So okay. So the reason why you do this is kind of because of the rule of I usually like to link this back into the rule of x plus y times x minus y. So what happens in x plus y times x minus y is you're going to have to time this one by one, and you will get x squared plus xy minus xy plus y squared. And then you remove this, minus y squared. So, and you remove this and you get x squared minus y squared. Now, since one of the, you get square root of 2's in these results. If you have a surd form and then you insert the numbers, as a surd. Let's just say, for example, we have x plus square root of y. And then you multiply this by x minus square root of y. You will get square root of 2 minus y over square root power of 2. And this would remove the radicals and gets you a nice number instead of a radical. So in this case, you just multiply it and get 5 times 2, 5 times 2 minus 7, square root of 7 over 4 minus 7. And now by doing that, you now have a nicer looking number and generally easier algebra to deal with. Okay, so I don't really know if I should explain the law of exponents because they're generally self-explanatory, like a to the power of m times a to the power of n equals to a n plus n. And this is because of the exponents. It's like kind of like saying a to the power of 2 times a to the power of 3 equals to a to the power of 2 plus 3. It's like if you expand it, you can obviously see why. It's kind of just because of how it naturally works. Well, I find it pretty intuitive. And it's also the same with am over an, a to the power of n. It's kind of like saying, for example, if it's a to the power of 3 over a to the power of 2, that's like saying a times a over a times a. So you just cross it over and get a to the power of 1. So for this, saying a to the power of 2 times to the power of 3 is kind of like saying that for every two a's, you have 3 of them because you multiply itself by itself, on itself. So you just multiply them and get a to the power of 6.
Alright.
Mm-hmm. Do you have any
No,
questions? Huh?
no, it's all very straightforward.
Yeah, that's why. And then finally, we have. Oh, I haven't explained about the. I haven't explained about the standard form and the a to the power of -1. This is so if you have a to the power of -n, it's kind of like saying my a to the power of -1 times n. That's also so that's like a times a to the power of n. Oh, this is. Oh, that's weird. Well, wait, if it's like, oh yeah, if it's okay, yeah, no, it's supposed to be. It's supposed to be like this. So it's kind of like, huh, kind of like, and yeah, it's like this. And then for standard form basically just requires you to have one digit times 10. So to simplify things up and to not have like too many zeros or too many for example like 25 0 or 0 0 0 75 to prevent to having like these whack formats because there's either like too many zero or too little zero or like not a uniform standard. They have this thing called standard form, and basically they need to have the a in the range of 1 to um to 10. So like they need to have a as a single not more than a single digit. Yes.
Alright.
And then have the rest of the decimals or the zeros in forms of 10. So you can just see the k. So for example, if you have this number, then you turn it into 7.5 times 1, 2, 3, 4 times 10 to the power of -4. Well, for this one, since we have 1, 2, 3, 4, 5, 6 zeros, we turn it into 2.5 times 10 to the power of 7. So there's 6 zeros, but then you have to like
Yeah.
move the decimal dot here, so you add another 0, and that turns into 7. I mean, that's all pretty much it. So we can just do practice questions, I guess.
Sure.
Okay.
One sec. Alright, I'm back.
Okay. Yes. Actually, you just do
One question.
this. Each of these. Wait, this is. Oh, and this one is actually blue. I guess we can do these. Still do 1, 2, 3, 4, 5, 6, 7, 8, 9 questions. So the answer is 1 over 3 to the power of 3. Second one, 3 to the power of 3. The third one, you cross them out and you get 5x over x squared. But 1 to the power of 3 over 64 of s over 3. And then this one, you just do this, you just move this up. And then for this one, becomes 8 to the power of 6 times b to the power of 7. For this one to write a decimal number of it, you just turn it. You just add 10 zeros. I think that should be right.
Yep.
And then for this one, you just turn it into this amount. This one turn it into 10 to the power of minus 4 m. And then for this one, since they have the same base and exponent, you can just do 4.3 minus 1.5, and that results in 2.8 times 10 to the power of 9. I think that's pretty much it.
For question 7,
Mm-hmm.
can you write it as never mind, sorry.
You mean write it without the fractions?
Yeah.
I mean that's also fine. It's just they don't really require you to do it. You can write it like 1/64 times t times s to the power of minus 3, but they won't give you points for it. That's just it. So people usually don't bother doing that.
Okay.
I mean, this is pretty much the same thing. So I guess that's pretty much it for today's session.
Nice.